All right, so everything that we learned in the last section, graphing, sinusoids, is going to now pay off in the next section, because you're probably wondering to yourself, why on earth are we studying these sinusoids, other than to extract the undescribable pleasure that we get when we sketch them, right? I mean, that in itself would be sufficient enough as an end. But man, you know what? Certain things in real life can't be described adequately by a polynomial or by an exponential function or a log function. Because some things in life ebb and flow, and ebb and flow, and flow and ebb. Like what? What? A river. Oh yeah, a river can ebb and flow. Usually, yeah, especially the one called the Guadalupe that is controlled by the Corps of Engineers when they control the flow from the dam. So that would be one that doesn't ebb and flow regularly, right? You also have those 20-year, 100-year floods that come every 10 years that cause the rivers to swell. So that would also ebb and flow, but not at a regular interval. Okay, those are kind of just random times. What do you know in the real world ebbs and flows or cycles through at regular intervals? Ferris wheels. Tell me more. What about a Ferris wheel? The Comal County Fair comes and goes once a year, and with it they bring a Ferris wheel. Is that what you're talking about? The Ferris wheel comes and then the Ferris wheel goes? Okay, well that's true. And also maybe the riders on the Ferris wheel, if you measure their height above ground. They go up and they go down. Very good. That was a great example. Someone else said something over here on the left. What was it? Sinusoids? Yeah, the graphs themselves go up and down. But what can we model that follows that type of behavior? In physics, they call it simple harmonic motion. That's what's highlighted down there. Simple harmonic motion. What'd you say? A roller coaster? Yeah, I mean, yeah, if you look at the cosine graph, that would make one heck of a roller coaster, right? At regular intervals, up and down, right? So, yeah. How about, I don't know, have you ever heard of a high tide, low tide? Yeah, the tides come in, high tide, they go out at low tide. What causes them to do that? The moon, right? Because it has different gravitational pull, bless you, at different times, bless you, in our orbit. So it's kind of like if you were standing still with a glass of water, the water would be fine. But if you shake your hand left and right a little bit, that water is going to start sloshing. That's the effect the moon has on the Earth. It has different gravitational pulls, and so it sloshes our water around a little bit, and that's high tide, low tide. And it happens pretty regularly, doesn't it? Yeah. Okay, so that's called simple harmonic motion. We're going to talk about the Ferris wheel, coincidentally enough, that Peyton was bringing up. Maybe he was reading example 1, which is smart to read ahead. It's smart to read ahead. If you don't know the answer to something, it's smart to be able to know where to go to get that answer, rather than just to sit there and be content with being dumb and ignorant, right? You don't want to be willfully ignorant, which is much worse than being unwillfully ignorant, right? Those people are too ignorant to even know they're ignorant. You want to be willfully intelligent. The Ferris wheel at the Comal County Fair. Who's ever ridden that? Yeah, it is kind of scary, yeah. Only because you wonder if they have all the bolts in there and all the bolts tightened. Yeah, and it creaks as it goes up there, like crate, oh, here we go, we're going down. That's what makes the Ferris wheel exciting. Now, normally Ferris wheels are rather boring, unless they're super big and you're afraid of heights. But at the Comal County Fair, it's a thrill ride, simply because you're not sure if it's going to hold together, all right? But every year I go, I ride it, just to make sure my dad is always up to date. It's a 3-minute ride. And I exaggerate that. It's like a 1-minute ride. You know, they don't care. It's a 1-minute ride. We'll put a 3-minute ride here. That takes its riders on a thrilling ride up to a maximum feet of 105 feet and a low point of 5 feet. So, you know, there's that little loading ramp you get on there, and you're 5 feet above the ground at the lowest point. Assuming that the Ferris wheel rotates at 6 RPMs, 6 revolutions every minute, and that a rider starts his stopwatch, that would be me, okay, as the ride starts at its low point. So I always let people get in front of me until it's all full and I take the last cart. So that way I can start at the bottom, you know. Otherwise, they move you up and you're kind of waiting for other people to get on and you're sitting there, right? So I'm the last person on. I'm starting at the very bottom. The ride goes for 3 minutes. I start my stopwatch. It's rotating at 6 RPM. We can model my height, your height, in the butt of the seat, not the bottom of your legs, because everybody's legs hang down a little bit differently. But where your butt hits the seat, we're going to model that height, the height of your butt above ground, as a function of time, right, for those 3 minutes. And it should be consistent, right? It should go up to 105, come back down to 5. It should go up to 105, should come back down to 5. It should go back up to 105. Okay. And then they spray it out with a hose. It's like, next. That happened to me on the zipper one night in high school. Yeah. The zipper, you know, it turns a lot. And the people in front of me, I waited a long time. It's a popular ride, right, on Friday night. And then the guy threw up, sprayed it out with a hose, and next. I got in. Yep. It was pretty bad. It was wet. And of course, they didn't get all the chunks, you know, so there were still chunks in there. And then you flip upside down, the chunks fall on your face. And then you throw up, and then it's just, yeah, one throw up leads to another. Anyway, Part A. Sketch the graph of the rider's height above ground h in feet as a function of time in seconds since the rider started his stopwatch. So, for these applications, we're typically going to start with a graph. If we can sketch the graph, as you very well know by now, we can then very, very easily come up with an equation, right? Because we have everything marked. So, let's go ahead and sketch the graph. I'll need a set of axes. So I'm going to do it like this. Okay, and I'll extend this out maybe a little bit further. Now, because we're measuring the rider's height above ground, now we have h of t in feet on the y-axis. Now, why can't we just arbitrarily label the y-axis as feet? What is the y-axis normally when we sketch a sinusoid? The y-axis is a sine or cosine ratio, right? Which, remember, is the ratio of either y to r or x to r, which, remember, are two sides of the right triangle. And if the triangle sides are measured in inches, so is the radius. What happens to the units in a sine or cosine ratio? They divide out. So all of your trig ratios are unitless. All of your trig ratios are unitless. And because they're unitless, we can give the y-axis, which has no units, any units we prefer. What are the units normally on the x-axis for the sinusoid? Yeah, pi, 2 pi. Those are the angles measured in what? In radians. And, of course, what are the units of radians? None. There are no units. And that's why we can put time down here. And what did it say in seconds? Minutes. Because there's no units on the x-axis, we can call it the t-axis, and we can give units of minutes. That's why we have to be in radians. If we were measuring in degrees, the x-axis would be in degrees. We wouldn't be able to assign it minutes because it's already taken up by degrees. Because now it's unitless, we can give it any unit we want. Okay, that's cool. All right, so how are we going to start sketching our graph? Well, let's do the vertical axis first. If the vertical axis measures the height, what's the lowest our rider gets? 5 feet. So I'm just going to call this 5 feet right there. What's the highest the rider gets? 105, okay? If my altimeter was correct. Yeah, I think it was. 105. So there's your low and there's your high. From there, we can draw our sinusoidal axis. Yeah? Because the sinusoidal or central axis should be directly where in between those two? Directly in the middle, yeah. So if you bisect it, you could draw your horizontal line. Now, notice I'm only drawing it in the first quadrant because this is the t equals 0. That's the y-axis. Does negative time make sense in this problem? No. So our relevant domain, remember, anytime we have a word problem and we're modeling it by an equation, the equation itself might have a domain of all real numbers, like we know sine and cosine. But the relevant domain is, okay, the model is only good for what values of t? Well, we're starting our stopwatch at 0. I'm including all of y'all now. I hope that's okay. I'll scoot over so y'all can fit in the seat. I think we're going to exceed the weight, max weight, which will make it even more exciting. Okay. All right. Can we label that number? Can we find out what that number is? What's halfway between 5 and 105? 50? 55. Good. Now, the easiest way to figure out a midpoint of two numbers is just to find their average. Okay? Add them and divide by 2. 105 plus 5 is 110. Half of 110 is 55. We already know one of our letters in our equation, don't we? Or two of them, really. What's our d value? 55, right? Remember, the sinusoidal axis is your d value. Do we know the a value already, too? The a is the wave height. It's the distance from the central axis to either the high or the low. It's 50, right? All right. So, man, we're almost there. We just need like a B and a P and an R and D and all that. Okay. So let's go ahead and draw it first. I start at a low point at t equals 0. So I'm going to go ahead and just put a dot right there. Now, because I start at a low point going to the right, there's only one place I can go, right? And it's to the axis. So let's establish our scale. I'm not sure what the number is going to be, but I'm going to put that as my next critical value. And now I've established that distance between the y-axis and my first critical value, which is also the distance between two consecutive critical values. So now I'm just going to go out here, and I'm going to make marks that are about the same distance away. And I'm going to go up pretty far here, more than one cycle, because remember, this is a 3-minute ride. Now, I don't think I'm going to go out all 3 minutes, but, you know, I'll go out farther than usual. All right, so all of those are about the same distance apart. So I can actually finish the graph before I even know what the numbers are. So if you want to do that, that's fine. We're just oscillating now, right? High axis, low axis, high axis, low axis, high axis, low axis. Boom. And if you want, you can even connect the dots now. You can imagine that you're riding the ride. Whee! Yay! So much fun. Wait, where's the carnival operator going? How are we going to get off? He's going to the bathroom. He'll be gone for an hour. Okay. I hope this thing runs out of batteries. Yeah, I don't think it's run by batteries. There we go. All right. There it is. Now notice I'm not extending it past 0 and drawing an arrow. Why not? Yeah, negative t values don't make sense. So there's a pretty version of the graph. The x-axis is kind of acting like what in real life? If we're measuring the height above ground, the x-axis is acting kind of like the ground, right? So if you want to come back with like green and put some like sprigs of grass right before it gets all trampled, you know? Yeah, there's some sprigs of grass. And then there's mud everywhere, right? Okay, so you get the idea. What are we missing, though? We're missing the important x values. Because if we're going to use this model, the independent variable, time in this case, is very, very important. So how are we going to just figure that out? Well, let's come back up here. Is there any information there that gives us a clue as to how we're going to label the x-axis or the t-axis now? It's a 3-minute ride. Okay. So, man, that's good. I know when to quit putting my values, but what's going to help me mark those values? Do I just come out here and say that's 3 minutes? No, because that's just once around. I think it goes around more than once in 3 minutes. Is there anything that tells us how fast it spins? That's kind of what we need, isn't it? 6 revolutions per minute. Oh, that's good. I think we can use that. Come over here. We know that it spins at 6 revolutions per 1 minute. What is that a measure of? It's a measure of rotation per time. It rhymes with angular velocity. Angular velocity. Very good. That is a measure of angular velocity. What letter did we use for angular velocity? Not W. Omega. Omega. That's the angular velocity of the Ferris wheel. Can I use that to help me find the period? Let's think about this. The angular velocity tells me the number of revolutions per unit of time. That's essentially like the frequency. It acts kind of like the frequency. Cycles per minute. Frequency tells you how fast something is going per set unit of time. I want the period, which means I want how many seconds it takes to make one revolution. That's what I want. Or I guess minutes in this case. That's what I want to know. I want to know the length of time it takes to make one revolution. Well, how can I get from revolutions per minute to minutes per revolution? It rhymes with clip it. Flip it! It's the reciprocal, isn't it not? Or is it not? Sorry. Isn't it not? Never? Not? Okay, so I have 6 revolutions per 1 minute. That's the same as 1 minute per 6 revolutions. Don't! Okay, well that's not good. So let me do this. That is 1/6 of a minute per 1 revolution. Is that the same? Yeah. So how are the frequency and the period related? Yeah, they're reciprocals. The angular velocity is the frequency. It's the reciprocal of the period. So is that enough to tell me? What am I supposed to measure it in? Sketch the rider's height above ground feet as a function of time in what? Seconds. Okay. So if I have now 1/6 of a minute per 1 revolution, how can I convert from minutes to seconds? Yeah, 1 minute is 60 seconds. And stoichiometrically, great adverb, I need minutes to be in the bottom. So, and now I'm left with seconds per 1 revolution. What's 60 times 1/6? 10, right? 10 seconds per 1 revolution. There you go. There you go. That's what we want. If you're given the angular velocity, the reciprocal of that number is your period. So 6 revolutions per minute, that's 1/6 of a minute per 1 revolution. Oh, because I wanted to make my denominator a 1. Okay, I needed to make that a 1. Because what is the period? The period is defined to be the length of 1 cycle. And cycle is another word for revolution. Okay? Now, when we say length, that could be in radians, or in this case, it could be time. The time it takes to make 1 cycle. So 1 divided by 6 is the same as 1/6. Or you could think of 1/6 divided by 1 as 1/6. Okay? Whereas frequency is the number of revolutions per single unit of time. It's just a different way to measure it. Okay? So there we go. If you're given the angular velocity, the reciprocal of that is the period. All right, so now that I know that it takes 10 seconds to make 1 revolution, I can come over here. If I started at a low, it should be 10 seconds to return to the low. So I can call this 10. And call that 10 right there. And now we could bisect that to get 5. And bisect that to get what? 2.5. I put time in minutes over here on my axis. That's because it was given in minutes. But it said to do it in seconds, which actually makes a little bit more sense. We don't want to use fractions. What's the most important number on this graph? 2.5. Every mark now that I've already laid down is 2.5 apart. So let's impress our friends and count by 2s and 1/2. 2.55. What comes next? 7.5, then 10, then 12.5, then 15, 17.5, 20, 22.5, 25, So So I went out pretty far, but I only went to 25 seconds. This graph is really, if the right is correct, it's going to go all the way out to how many seconds? 180, right? So definitely you don't have to draw all of the cycles, okay? But I would say draw more than one. In this case, I have, 2.5 drawn? All right, so now that we have the x-axis all labeled, and we have it marked with the time in seconds, height in feet. So you do want to label your axes. Now I can say, okay, I did part A. Oh, part B, bring it on. Assuming, that's dangerous, right? You know what they say when you assume, right? Okay, but the instructions say to be one, so assuming that h is a sinusoidal function of time, write a particular equation. Confirm your results by Googling it. By graphing your equation in your graphing calculator in the window in which you sketched. Okay, that just means write an equation. Part B, write an equation. Now, some of y'all are really good at writing equations. Some of y'all still really are not good at writing equations. You write expressions. An equation has an equal sign in it, doesn't it? That's why it's called an equation. Now, our equation is a name equation. So, what do we want to call our equation? F of x, y. What makes sense here? H of t makes sense. Yeah. The height above ground as a function of time. Where you are above ground depends on how much time has elapsed. Is that correct? Time is your independent variable, and the height depends upon the time. And, of course, how fast the carnival operator spins it. Okay, so here we go. Is it going to be a sine or a cosine? Yes, right? Yes. Okay. Hey, it could be a cosine, but if I don't want to have a phase shift or a horizontal shift, notice that t equals 0, I'm starting at a low. The tissues are over there. Which function starts low? Negative cosine, which would be negative Clahal. That's what you're trying to say. Yeah. So negative cosine. Yeah, you were close. You don't really need to know negative Clahal. Just Clahal. Just know that if you start high or low, it's cosine. High is positive, low is negative. So, speaking of down, this is negative. What's the amplitude? 50 cosine. Now, before we go any further, what significance does 50 have in this problem? It's not only the amplitude, but as pertaining to the ride, it's the what? It's the what? The halfway point of ground? It's the what of the Ferris wheel? It's the radius. Good. All right, that's the radius of the Ferris wheel. It's the radius of the Ferris wheel. Okay, cool. And we know that the center, the axle of the Ferris wheel, sits at what height? 55. Yeah, the central axis is the axle. Okay, the central hub. Okay, cool. So now we need the B value, don't we? Now here's the thing. This is super important. When you're given the equation, you're staring at your B value. In order to graph it, we convert it to the period, yes? It works in reverse. If we're starting with the graph, we don't get the B value directly. It's the number of cycles in 2 pi, but that's really hard to discern. Rather, we get the period from the graph, and we convert it to a B value, right? So if the period is 2 pi over B, then B is 2 pi over P. It's really the same equation. Do we know what our period is? What is it? 10. Good. So if the period is 10 seconds per one rotation, then B is going to equal 2 pi over 10, also known as pi fifths. Good. You got that? You get the period from the graph converted to bless you, where bless you starts with B. If you're given the equation, you start with B and you convert it to P for plus, period, exclamation point. All right. Now, normally we have a phase shift, but because we're starting at 0 at the low point, all we have to do is put not X, but what? T, right? And then plus our D value, which is what? 55. Okay, so there's one version. That's probably the simplest one to use. Let's do one in terms of positive sign. What the hey? So positive 50 sine of pi fifths, open parentheses T plus or minus something something plus 55. Positive sign. What's the smallest value of T to get me to a positive sign? 2.5. Positive sign is on axis going up. Sign always is on the axis. Positive is going up, negative is going down. So that would be minus 2.5. Now, if I graph both of those equations in my calculator in Radian mode, and I use this window, they should be the same, right? Let us see. If you have a calculator, play along. There's plenty nearby if you need to grab one. They're all over the place. There's some over here. They tend to stack them up on my desk over here for some weird reason. They think it's funny. There's some under the desks. They haven't fallen on the floor. That one might work. These are broken. Does that one? Turn it on and see. Yeah, okay. It'll load. Yeah. All right. All right. First things first. We're going to hit a sine or a cosine button. So what should we do first on our calculator after we turn it on? Check to make sure you're in radian mode. If you're in degree mode, I'm just going to laugh and laugh and laugh while you cry and cry and cry. Yeah, I know. It's real nice. But at this point, you deserve those chuckles because you should know better. Right? Mode. Come down here. I'm in radian mode. Whew, that was a close call. Now you go to y equals and get rid of anything that might be in there. Flush, flush. Okay, let's type in our first one. Negative 50 cosine. We're going to use x instead of t. Okay, so it's pi fifths. If you want to use the horizontal division bar, I like that. Okay, so that makes it look pretty much like what we have, pi fifths. And then click to the right, just put x instead of t. That's the default independent variable in the calculator. And then plus 85. Now don't hit zoom 6 and don't hit graph. I guess it didn't work, sorry. All right, now you go to, there's two over there. Don't play. Now we go to window. Double check, it looks good. Now we go to window. X min, I like to do -1, just so we could see the y-axis instead of starting at 0. Our graph goes out to 25, so let me go to 26. Oh yeah, just one more. And then your x scale, you can leave it at 1. You can turn it to 0, which means there's no marks. But what are we counting by? Yeah, if you want to do 2.5, it doesn't hurt. I usually turn that off to 0. It doesn't really matter. Now your y min, again, we don't need to see below ground, but I'm going to put -1 just so I can see the x-axis. And if our high value is 105, I would go a little bit more than that, like 120, just because the calculator likes to use the top of the screen to put information, so we don't cut it off. Now your y scale, we just hit 0. We don't need marks on the y-axis. Okay? And leaving it at 1, you're going to get like 121 marks in a small screen. You're going to get fat axis. You don't want to do that. Okay? Now hit graph. Ooh, ah, ooh, ah, ooh, ah. You can almost feel like you're writing it, huh? Now, compare that graph to our graph. Oh, that's Apple Music. Compare that graph to our graph. Whose is better? Yeah, there's no comparison. Ours is much, much better. Now, before we use it, we should probably verify. It looks like it's right. Let's come over here to 12.5. At 12.5, we should be at 55 going up. You see that? So let's come over here to the graph. Let's hit trace button, and then just type in 12.5. And let's see if it's at 55 going up. No, I hit Stupid. Hit enter. Hey, it's at 55 and it looks like it's going up. Right? So that's an indication that we are awesome, right? That we're correct. All right, now let me go ahead, if you want to do the other one, and say like, I don't like cosine, he's kind of a bully, so I'm going to use sine, positive 50 times sine. You could just do pi divided by 5 like this, but now open parentheses, x minus 2.5, close, close. That's not just me describing my daughter's closet. That is closing parentheses. Okay. 55. Now I hit graph and ooh, ah, ooh, ah, ooh, ah. You got to ooh and off pretty fast, right? It's the same. It's traced over. And again, you can go to the table to verify that. Second graph, it's the same values, right? So another indication yet that we are still, like we had any doubts that we're still awesome. Now notice they actually get very different numbers way down here in the back. That's 5.2, and the other one's 5.4. Okay, because it's using different functions for sine and cosine. But notice to all these decimals, it's the same, and that's pretty accurate, right? So the rest of it is just kind of a overflow error, or programming flaw, but it's pretty good, better than I can do. Okay, so now let's go back to the notes. It says part C. Now that we have the model, we don't just walk away. That's what we did in the last section. Kind of unfulfilling, right? Aw, so pretty. I want to use it. Well, now we get to part C. How high above ground is the rider at 48.5 seconds? At this time, is he going up or down? Okay, at 48.5 seconds. Is 48.5 an input or an output? Is it a T or an H value? T. So remember, with calculated problems, like we did for logistic, you got to show me H of 48.5 close. If you don't show that on a calculator, you get 0 points, okay? Now, does my window on my calculator, does it go out to 48? Oh, I only went out to 26. So if you try to do this from your graph screen, if you hit trace, and it doesn't matter which equation we're on, if you hit trace and you type in 48.5, it's going to be like, you fell off the roller coaster. Not responsible for injuries, dude. Okay? And it's like, go to. What's wrong? And it's like, you typed in a 4, idiot. So remember, you don't have to go to the graphing screen. Now, if you want, you could change your X max to like 50 and then wait for it to graph again. Oh, that takes a long time. So remember what we could do. From the home screen, we can evaluate functions. Hitting alpha trace, where's our equation? I'll use Y1. We have it in Y2 as well. Open parentheses, 48.5, and we don't even really need to see the graph. Boom! We're at 25.610 when you truncate, 1 when you round. And what are the units? Feet, right? Above ground. We're almost 26 feet above ground, people, at 48.5 seconds. Are we going up or down at that moment? We're going round and round. What do you mean? Going up. Yeah. How do you know if we're going up or down? We don't see the graph. That's the only bad thing. If I would have extended my window to 50, I could have seen exactly where it was blinking, and I could tell easily if it was going up or down. But I'm not going to give in now and go back and graph it now. I'm not a quitter. Oh, because 50 was high? Every 10 seconds, 10. Every multiple of 10, we're back down at the bottom, right? Oh, okay, so you can imagine that. Is there a way we could do it from the home screen still here? Probably. Yeah, how about this? Second enter, recall it. Come back in here and let's look into the future just a smidgen. 48.5, let's go to 48.6. 1/10 of a second later. That's not that long, right? Hit enter. Oh! 1/10 of the second later, I'm what, higher or lower? I'm lower. Is that enough information to discern that we're going down? Yeah, pretty safely. Now, it could have been that we still went up and we went around the top and came back down. But if you're still not sure, do this. Instead of letting 1/10 pass, type it in as, 5/1. Let 1/100th of a second pass. Then you compare. Are we still lower? From 0.6? Yeah. So that's how you could do it without looking at the graph. Okay? Because you don't want to have to wait for it to graph. So in actuality, it's coming down. So I would say in general, if you look 100th of a second later, just put a 1 at the end. Don't even change that. Just leave it as a 5 and put a 1. Then you're safe. Very unlikely you're going to pass around unless your period is really, really small. Like it's oscillating like, once every billionth of a second. Then you got to be careful. Okay? So let's just go ahead and say moving down. So on paper, we'll put H of 48.5 equals 25.610. And we'll say heading or moving down. Moving down. Or is it down or downward? Or downward dog? Moving down. We'll just say going down. Going down, moving down. How about going down? Going down. There we go. That'll work. Going downward, heading down, moving in the neck towards Earth. Okay. Are we done with example 1? No, hey, okay. Part D. At what positive time is the rider 88 feet above ground coming down for the third time? Well, got to read that again, like a Dr. Seuss. 88 feet above ground coming down for the third time. 88 feet, oh my gosh. Is 88 feet a T value or an H value? It's an H value. So let's do this first, part D. I'm going to say H of T equals 88. And then underneath there, I'm going to put T equals, because I'm going to answer it. This is the one, unless we're not going to do it by hand, this is the one when you have a Y value, remember, how do we solve it? We graph it. Okay, I'm going to turn this one off. We graph it, and we find where it intersects. I'm going to go down here so I can use some color. So 88. Now, if I hit graph, here you may have to adjust your window. I want to be 88 feet. I'm 88 feet right there. Is that what we want? That's 88 feet going up for the first time. There's 88 feet going down for the first time. I want to be 88 feet going down for the third time. So I'm going up, go down. Going up, stop. Bummer. Oh, it's right there. It's off the screen. What can I do? Change your window. Oh, I thought we were trying to avoid doing that. Shut up. Just do it. Now you can. You could have done that on the first one. So I'm going to go to 35. You wait. I'm waiting. There you go. My life. Okay. So up, down. Life's like a jump rope. Up, down. I played that song this morning. It was October. It's good. All right. So it's right there. See it right there? Right there. That's the one we want. That's it right there. So how do we find points of intersection? Second trace number 5. Okay, is this the first curve? Sure. Is that the second curve? It puts you on 88? Yeah. Is this my guess? Nope. If I hit enter, it's going to find this one. I want to find, that one. Whoa. Yeah, no kidding, right? Right there. Well, stop. You can click this, and then it keeps remembering how many times you clicked it. How about right there? Looks good? Now hit enter, and voila, there it is. T equals 26.352 truncated or 3 rounded seconds. Okay? Now, what if you didn't want to change your window? What if I went second trace, number 5, enter, but I'm like, you know what? I'm not going to change my window. I'm not going to waste my life waiting for my calculator to regraph both curves. My gosh, I'll never get those seconds back ever again. So I'm just going to find this one. This is going down for the first time. Shazam! 6.352. How far away is this next one from that one. 10. What is 10 in this problem? The what? The period. So if this one's 10 seconds away, the next one, which is what I want, would be 20 seconds away. What's 20 plus 6.35? 26.35. There you go. So you don't have to change your window. You can use the periodicity of these functions, these simple harmonic motions, to find the ones you want. Okay? That's an FYI. All right. We're going to have to stop right there. But look at these, just a preview of what Monday's going to bring. During the 3-minute ride, for how many seconds was the rider above 100 feet? Oh, my gosh. That's like, they call that the death zone on Everest, when you're above 100 feet. Well, on Everest, they call it above 24,000 feet. But that's where your body starts to decay and die, you know. Yeah, it does. Your body starts to break down and die. So you can't spend too much time above the death zone. For this ride, we're going to say it's above 100 feet. And then look at this. We're going to turn it into linear velocity. What is the linear velocity of the rider in miles per hour as he goes around the outside of the Ferris wheel? We will continue on Monday. Have a fantastic 3-day weekend. No, it's only 2 days.